Okay, so for what I did for now was only topology. I didn't use the metric at all. There is one more condition that doesn't use the metric. It's a boundary condition. I will do a little bit mixed like organization of the setup of the formulation. So I will not do only what is inside and then on the boundary, but now we will do the boundary, one of the boundary conditions, which doesn't require any metric as well. So now we'll do the Neumann boundary condition. For that, consider gamma n, which is set of dm, a d minus 1 dimensional surface so this is Neumann boundary. And a prescribed flow rate. Again, this is in absolute terms. So this will be G from the interval. So for any point of time, we have d minus 1 on gamma n. This is Gn. And Gn is the same dimension as the flow rate. So this is again amount per unit of time, the velocity of how amount flows. And the Neumann boundary condition because Gn is usually prescribed, so it's given by the user, as to say. It may be given as a density. If it's given as a density, some translation has to be done. For example, if it's per unit area, it has to be hot start, maybe something like that. But the Neumann boundary condition is given by the trace on the boundary of Q is Gn. So in vector calculus, usually you need to do normal multiplied by the exterior normal, but here because of the language, we only need to do a trace operator. And it doesn't require any metric, any unit vectors, anything like that. It's directly from the topology of the space. Okay. Now let's define a new class of variables, which are potentials. So the potential U is zero form. So with generic physical dimension y drives the diffusive part of the flow. So this is a new variable that is part of the model, and so for energy we have temperature, heat energy. We have temperature. For mass, we have concentration. For volume, we have pressure. And for charge, we have potential, electric potential, or voltage. Okay, let's go with electric potential / voltage. So this is what drives diffusive part of the flow. And so to formulate the relation, we need to separate the flow into diffusive and advective part if there is advective part term. So we split the flow into diffusive and advective parts. And so we have Q will be Q diffusive plus Q advective. So this is what we do. This is the quantitative way of saying that. So this diffusive and this advective. And the constitutive relation, this is not a physical law, it's material. So what was so far said is true, independent of the material, but the constitutive relation depends on material properties. The constitutive relation is given by T, so QD is kappa of delta star of U. This is things like that. First, so we have these operators, and here kappa is some is the conductivity. With regards to dimensions, everything is explained in the paper. I will not go in details about dimensions, but x. So kappa is of dimension x, y to the minus 1. Of course, d is 3, but I want to be general. So we have length 2 minus d and time to the minus 1. This. No, I will not write brackets. And kappa is, so it's some function, usually positive definite, but let's not go into so much details. So it takes, this is from 0 go to d4, and this becomes d minus 1. And we do some kind of coefficient on it. So for isotropic material, it's just some single constant. It's multiplication of it. But in general, it's some operator, not differential operator. Is the conductivity of the material. Okay. And this is usually explained from statistical mechanics. So how it's explained, so you have, this is the temperature, but it becomes a D form. So the potential, so if you have some surface here and two volumes, and if there is more in this, more stuff or energy, something like that here than there. So this has, for example, U tilde plus, U tilde minus. So we have something like Q with respect to S is proportional to U tilde plus minus U tilde minus. This is discretely more clear. Continuously, you have to make some infinitesimals because you have differential operators. But the idea is that you go from plus to minus. So if there are more molecules here than here, the spontaneous movement means that we have flow in that direction. So if U plus is bigger than U minus, if U plus is bigger than U minus, we get flow in that direction. And this is the quantitative version of this relation. And the hot star is used in order to dimensions to match. Yeah, so this is similar to what's in the continuum. There it will be like some Q tilde will be minus kappa some nabla of U. But here the sign is different because the operators have a little bit different signs, but it's the same idea. Okay, so this is in vector calculus. It's not what we do. For advective flow rate, which I don't have in my code, but in general, it can be done for advective flow rate. We need volumetric flow rate V. It's a D minus 1 form, and its dimension is what is it, XL to the minus L minus D, something like that. I think so. Yeah, no, sorry. Totally different. So it measures how much volume passes for a unit of time. So how much volume passes through the surface per unit of time. Okay, this is what it is. I have some equation here, but the flow rate is then defined as star D of Q wedge product with V. So it's like the total amount multiplied by the hot start multiplied by the velocity, something, the flow rate gets you the advective term. Andrei doesn't agree.
What is Q?
Is the amount, total amount. That's why we, so I think
Where is D? D is D minus 1 from?
yes.
So you first apply hot start to Q.
Yes. To make it a density and then multiply by the velocity. Like energy density times velocity is advective flow, something like that. Okay, and to finish, we need to relate potential with the amount. So we relate potential with amount by the material coefficient of volumetric capacity. I think that is how I call it. Only capacity. Volumetric capacity. So this is like C rho for energy. So this is, I call it pi x. So it's a dimension x to the minus 1, L to the minus D. So all material coefficients have dimensions like in usual vector calculus, and the reason is because these are measurable properties. Some averages on bodies, but the flow rates, energies, things like that, they are defined by the model, and in vector calculus they use densities, but I decide to use absolute quantities, and so they can be whatever dimension I want. At least it should be compatible. The laws have to have compatible physical dimensions and have to be compatible with standard formulations. But P and kappa, they have the same dimensions as in vector calculus because they're measurable. And P is from, it can be made for zero forms as well, but I made it for D forms. So there is a version for P for zero forms. I forgot to call it for Q kappa as well. So we have P tilde for zero forms as well. C infinity. They're related by P tilde composed. So star zero composed with T tilde is P tilde P composed with star zero. I also forget to say that we also have kappa tilde. This is kappa, but it becomes for I to omega 1m to omega 1m. So that kappa tilde star 1, kappa tilde is kappa composed. Sorry, this is not right. This is star 0 and this is star d. And here is star d minus 1. And here is kappa composed with star 1. I forgot that I should make it there, but so sometimes because in different formulations we work sometimes with 1 forms and 0 forms. Sometimes we work with d forms and d minus 1 forms, and that's forms. Sometimes we work with d forms and d minus 1 forms, and that's why I introduced both operators. They look like the same. The star operators, they just make dx to dy dz, once to dx dy dz, something like that. So they don't do much computation in some sense. So I introduced the capacity, and let's write the law for it. So I have dq dt is p of star 0 du dt. So if this was c times rho is the density and c is the capacity per unit mass, this will be like in standard formulation for heat equation. And this also can be written as star 0 p tilde of du dt. Okay. And finally, let gamma d be the other part of the boundary. It is not the set difference because they can interlap other part of the boundary, i.e. gamma d united with gamma n is dm, and gamma d, the dimension of their intersection is less than d minus 2. So, for instance, if I have a sphere and this the and its boundary is I have a its boundary is the sphere, and I take gamma d to be the southern hemisphere, gamma n to be the northern hemisphere. Their intersection will be of dimension 1. So S1 is the gamma d intersection with gamma n, and the dimension of S1 is 1, which is less than 3 minus 2. So these are two-dimensional boundaries, and their intersection cannot be two-dimensional. So they have to cover, in some sense, the space.
So, on the right, the third line from the column, is that star D composite by zero, or is that a zero?
This is star D, this is star 0. Yeah. Yeah, D looks like 0. Sorry about that. Anyway, can I erase this part here? So when we summarize everything, we get the following. So the summary of our equations. dq dt is f minus this is d minus 1 q, and it is also this is also dq dt is also star 0 t tilde du dt and p star 0 star d, this is p star 0 du dt. Alphonse, maybe I made a mistake previously, I'm not sure. P0 and then star D. It should be P0 on both sides, and the kappas should be all the same dimension. I think they should be kappa 1. I'm not remember. But anyway, we'll do this in the last lecture when I do different formulations, and we'll see which is the right one. Q is Q D plus QA. So this is diffusive plus advective flow. Here QD is kappa D star 0 of U. This is the what's called this is constitutive flow. Yeah. QA is star D Q OH with V. Oh, I forgot to say that we have Dirichlet boundary condition. this is the Dirichlet boundary, but I forgot to say Dirichlet boundary condition. Okay, I just write it and then trace of gamma n of q is gn. Trace of gamma n of gamma d of u is gd, and u of t0 is u0. So this is initial condition. So u0 is from it's a zero form. It's omega 0 m. And this is Dirichlet boundary condition. Here, I don't have place, but I will write GD is a zero form on the boundary. Of gamma this way. So this is the prescribed potential. This is prescribed potential. So this is given, and Q, QA, QD, U, these are unknowns. In general, of course, there are relations between them, and in the different models, we destroy, in some say, substitute some of the variables. So if you substitute Q, big Q and the small q's with you get the primal strong model. So primal strong model. So substituting Q, QA, QD from U. So we have that P star. No, I write it maybe in this form. Let me see what I have written. Nothing. It's better to be in zero forms, maybe. P. So star 0 of du dt. No, sorry. P tilde du dt is, so this is here, and if I put this on this side, it will be star d of dq dt, which is star d. Yes. So f is known, q is unknown. F minus d minus 1 q, and this will become star d of f minus star d minus 1, and then I substitute q with qd plus qa, and qd is kappa d star 0 of u minus star d of q. Star d of q, which with v. So if you assume that So we have equations relating the derivative of u with the derivative of q, and we can assume that it holds without derivative. Assume that p tilde du of u times u is star d of q. And then we have p tilde du dt is this is this one. This is right this one. Star, and I don't know, but I always write the stars in the wrong way. So this is star d of f minus star d dd minus 1 kappa dd star 0 u minus star d of q. So this is minus p tilde u with v. This thing here, this should be so if I replace this, this should be I'm not sure about the sign, but this should be star d of f plus or minus, let me think about it, kappa tilde no, this is that way. This is how I will keep it, maybe. Yeah. I have some, maybe one manufactured example.
Earlier you defined QA as positive star ZQ.
Yeah, but this is the whole is with minus. This is I have sorry, I have d minus 1 as well. So this is d minus 1. And star as well. Yeah. Oh no, sorry. So yeah, this is in the brackets, and when I expand, I will get minus star d of this here. So I have this one. Let me give manufactured example. Example for steady state. i.e. du dt is dq dt is 0. So we have 0. So we have, we can remove the stars. We have f is equal to, we remove the stars. So we have d minus 1 kappa and d star. And v is also 0. Without advection. And this will be f. So consider M. Let M. This is not strictly a manifold because the boundary has corners. This is a cube, and cube has 8 corners. But at least when you don't do things on the boundary, it works. And say U is U x y z is x squared plus y squared plus z squared, and let's say kappa is, I don't know, but it's constant 2. Maybe it can be 1, but I decided to be 2. And so then Q is minus kappa of star 1 d0 of u. So yeah, this is kappa tilde. This is it's kappa. This is another way of calculating Q, and this is minus 2 times star 0, and this is the gradient. So this is star 1, sorry. 2 times x dx plus 2 times y dy plus 2 times z dz. And this is 4 times. So this will be x dy dz with minus plus y dz dx plus z dx which dy. And f will be d2 of q. Why? Because the right is 0 and f equals d of q. And this means that this is minus 4 times the divergence multiplied by the volume form. So this will be minus 4 times 3. So this will be dx plus dy plus dz dx which dy which dz, and this is minus 12 times dx which dy which dz. And we can include some boundary conditions. So what I do in the paper, I introduce some manufactured problems, give some boundary, calculate, okay, U on the boundary should be something, the temperature prescribed. For example, I'll calculate it on some phase, and then I calculate the trace of Q on the boundary, and they give also this as a initial condition, and then apply the CMC which you do later. But so I have continuous problem with exact solution, and I discretize the input, apply the combinatorial mesh formulation, and compare them. This was easy to be much easier to do with vector calculus. It's more interesting if I did on a sphere, which we can use. I don't know how to do with vector calculus easily, but with exterior calculus, it's not that hard because we have all the calculations done before. But this will be done maybe at the last lecture, because next time I will start with meshes. And the last lecture I will introduce the discrete model, which is almost the same, and the weak formulations, primal weak and mixed weak. And then maybe show other examples, primal weak and mixed weak. And then maybe show other examples and how I test everything. Okay. Any questions? Yes. So this is so in this equation we give f to be like that. We say v is 0. It's a steady state problem. We say kappa is 2, and we have to give some boundary conditions by applying q and q on the respective boundaries. But I will not do that. Okay, I am finishing.